Hello everybody, this is lesson 5 of the lecture Macroeconomics. I will discuss slide 25 to 60 of chapter 2, the long-run development of economies. So far we have derived the position and the shape of the macroeconomic production function, this red curve here, the savings or investment function, this green curve here, and the depreciation curve, this bright blue straight line here. We can now start the analysis to what level the economy will grow if we start with a, let's say, historically given level of capital stock as indicated with the shortcut KT. T is a time index and means today, simply. If we assume that the economy has reached this level of the capital stock, the resulting GDP will equal YT. Under the simplifying assumptions of this Solow-Swan model, GDP is equal to household disposable income. The savings curve tells us how much of this GDP is saved and how much of this GDP is consumed, the remainder. The capital market equates savings with gross investment, such that the savings curve is also the gross investment curve. If we subtract capital depreciation from gross investment, we receive net investment. Net investment equals the number of new machines, production facilities and so on, which are added to the capital stock. Consequently, we can find the capital stock of the following period, t plus 1, by adding the net investment to the capital stock of the current period, KT. Like this. Now, the new capital stock is in this position. KT plus 1 is the old capital stock plus net investment of the old production period and results in this level of the capital stock. The length of this vertical curve here, net investment measured in a vertical way, is identical with the length of this curve here, as you can control with the help of a straight edge. Now we can determine the new GDP level of period t plus 1 and the resulting gross investment level as we did before. If we subtract capital depreciation from the gross investment level, we receive the new net investment level. Net investment equals the number of new machines which are added to the capital stock. Consequently, we can again find the capital stock of the next period, t plus 2, by adding net investment to the capital stock of the period t plus 1. And now this process repeats itself over a couple of periods. As we can observe, net investment the difference between the gross investment curve and the depreciation line, net investment gets smaller and smaller. When the intersection point between the gross investment or savings curve and the depreciation line is reached, net investment will be zero and the capital stock growth will stop. So K star is the capital stock level where capital stock growth and as a result also GDP growth ends. Net investment is zero in this point. This is what we have already called the steady state. To sum up, we can describe this adjustment process in terms of a simple causal chain. If savings equal capital depreciation, net investment is zero and the capital stock and GDP stay constant. So now we have found the mechanism which leads from capital stock accumulation to the steady state of the economy. The following slides and the lecture notes contain information about the production factors typically used in GDP production. We will now address the question what happens with the steady state of an economy if the supply of one of the other production factors grows. Let's assume that the supply of technological knowledge, symbolized by capital letter A, grows. As explained on slide 39, technological knowledge refers to the subset of scientific knowledge which is necessary to produce goods and services. The interesting question is now, does an increase in technological knowledge change the steady state capital stock? How do we have to change the position of the GDP production function if we keep the input level of all production factors constant with the exception of the input of technological knowledge? If we use more technological knowledge, we can produce with every level of capital stock given along the x-axis more GDP. This means we have to shift the production function upward, like this. So given the old steady state capital stock K star, we are immediately able to produce more GDP. Since additional technological knowledge makes the machines in the old capital stock more productive. We can call this the primary effect of a larger supply of technological knowledge. But now, as a result of this first change, a couple of further adjustments will follow. First, we have to shift the savings curve upward. Since the constant savings ratio times a higher GDP causes higher savings volume for every level of the capital stock. If we leave the old curves aside, the diagram becomes somewhat clearer. Since savings are equal to gross investment, the difference between gross investment and capital depreciation is now again positive. This means we have again positive net investment such that the capital stock starts growing again until the difference between gross investment and capital depreciation is again zero in this intersection point here. We reach then again a new steady state capital stock, which we call again K star. The difference between the GDP level reached thanks to the primary effect and the new GDP level is called or can be called secondary effect. The total effect of an increase of the available capital stock of technological knowledge can hence be split into a primary and a secondary effect. Like this. We can now also describe this adjustment process in terms of a causal chain again. The initial change is an increase of the stock of technological knowledge. This causes an immediate increase of GDP. This causes an increase of savings above capital depreciation. This causes positive net investment. This causes growth of the capital stock, which we have called secondary effect. The secondary GDP growth effect plus the primary GDP growth effect yield together the total growth of GDP due to the initial increase of technological knowledge. We have now found all the factors of influence which determine the steady state level of GDP. First, the savings ratio. The larger the savings ratio, the higher the steady state level of GDP. Second, the depreciation ratio. The larger the depreciation ratio, the lower the steady state level of GDP. Third, the other production factors. The more production factors are available, the higher the steady state level of GDP. To sum up, the Solow-Swan model explains what factors of production determine the level of GDP in the long run. The basic mechanism is accumulation of production factors which are accumulatable, like physical capital, human capital, technological knowledge, and public goods. If the Solow-Swan model correctly describes reality, an increase in these production factors should increase GDP and vice versa. We have already discussed this diagram in the beginning of this chapter. If the Solow-Swan model is correct, it should be able to explain these differences in the development of per capita GDP. As the following digression shows, this is actually the case. This digression is not relevant for the written examination. It shows, however, how we can apply statistical methods to test theories like the Solow-Swan model empirically. Consequently, even a quite restricted version of the Solow-Swan model with physical capital, human capital, and the growth rate of population can explain nearly 89% of the variance of these data. If we use an ordinary least square regression. If we would add more production factors, the explanatory power of the Solow-Swan model can be further increased. So from an empirical point of view, the Solo-Swan model seems to provide a useful description of the data. We can now also address the question what might have caused the lower GDP growth rate of Germany after the unification, which we have found on the diagram of slide 4 at the beginning of this chapter. An important factor that causes GDP growth is, according to the Solo-Swan model, the stock of physical capital. So it is natural to compare the growth rate of the stock of physical capital with the growth rate of GDP. The stock of physical capital is measured by the German Statistical Office on a yearly base. This diagram shows the yearly growth rate of the capital stock measured at prices of the base year 2010. Consequently, the impact of inflation has been eliminated and the diagram shows the real growth rate of the capital stock. To eliminate cyclical fluctuations and focus on the long-run development of the growth rate, I have calculated a moving average of the growth rate. In every year I have added the growth rate of that year plus the growth rate of the preceding 3 years plus the growth rate of the succeeding 3 years, and then divided the sum over 7 to receive the arithmetic mean of all 7 growth rates. The diagram clearly reveals that there is a long-run decreasing trend in the growth rate of the capital stock as we move along the time axis. This fits also to our observation in chapter 1, slide 43, that the share of net investment in GDP was about 17% in the year 1970 and 3.6% only in the year 2018. The German unification and the resulting investment boom in East Germany seems to have interrupted this trend in the 90s, but not changed it in the long run. If we now add the yearly growth rate of GDP, here also calculated as moving average, it becomes obvious that the decrease of GDP and capital stock growth rates happened nearly simultaneously, as we should expect from the Solo-Swan model. The diagram shows that the investment boom from the German unification has interrupted this relationship for a period of roughly 10 years, but meanwhile this interruption has been overcome and both growth rates lie close together on historically very low levels. Okay, so much for this lesson. In the next lesson we will discuss what the Solo-Swan model predicts in the case of exhaustible resources.